Sometimes it's easy to think of Earth as the center of our universe, but in fact, Earth and its star, our Sun, are sitting at the edge of a very large spiral galaxy. Our Sun is just one of billions of stars in a galaxy like the one you see here. Our Sun formed billions of years ago out of a giant cloud of gas and dust, like this very famous picture of the Eagle Nebula. This cloud, 4.5 billion years ago, as it collapsed, broke into many small clouds, and within nebula like the Eagle Nebula and the Orion Nebula, which you see here, embedded in them, are solar systems that are forming today. We can look at them with the new power of the Hubble Space Telescope, and we see within nebula like the Orion Nebula, at their cores, we see disks of gas and dust surrounding brand new stars. These are solar systems in the act of formation right now. But we can't go back in time to see how our own solar system formed. But what we can do is we can study cues for how our own solar system formed by looking at rocks that fall from the sky, meteorites, pieces of other worlds. Today, my colleagues and I, Dr. Serena Sorensen, Dr. Tim McCoy, and myself, I'm Glenn McPherson, I'm a geologist at the Museum of Natural History at the Smithsonian Institution, are going to tell you about how, by studying meteorites, we can learn about our world's origins and how all of the planets in our solar system formed and evolved. But first, we're going to go to Serena, who's going to give you information on how you can contact us with your questions as we might work our way through our program today. To you, Serena.
Good morning. I'm Serena Sorensen. I'm a curator here at the National Museum of Natural History. In fact, I'm the curator in charge of the National Rock and Ore Collections. But today I'm going to be doing something a little different than looking at rocks. I'm going to be hosting your questions here at this field trip, part 2 of the best stories from planet Earth. I want you to remember that we have a web page here that you can use that will give you additional information about messages from outer space. So be sure to call up the web page and you can extend our field trip experience. You can also call in. We have an 800 number. It's 1-800-556-1115. When you call, though, turn down your television set or we won't be able to understand your question. We also have email. We have an email address here that will be coming up on the screen for you. So you'll be able to send in requests right to this room via email. So here's our email address. It is outreach. Okay, we're going to go now to the Rock Gallery and take a planetary tour of our nearest neighbors in the solar system.
We're about to take a voyage through the solar system. Come with us now as we zoom from its icy outer limits to the blazing sun at its center. Our first stop is tiny, frigid Pluto and its companion moon, Charon. Pluto is so small that some believe it's actually an escaped moon of a larger planet. This beautiful blue world is Neptune, one of 4 gas giant planets that consists mostly of atmosphere and only a small solid center. The dark oval near its equator is a storm as big as Earth. Blue Uranus is nearly Neptune's twin. It is the only planet to travel tipped on its side. Saturn is one of nature's masterpieces. The vast rings of icy debris encircling the planet are 270,000 kilometers in diameter, yet less than 1 kilometer thick. Giant Jupiter, with its family of moons, is like a solar system in miniature. Huge swirling storms churn up its atmosphere. Active sulfur volcanoes color one moon, Io, yellow and red. Small cratered asteroids like this one inhabit the asteroid belt, the dividing line between the outer gas giants and the inner rocky bodies. Fascinating red Mars is the first rocky planet we encounter. Water once flowed here, helping to sculpt the long, dark canyon known as Valles Marineris. Small clouds mark the summits of Mars' giant volcanoes. its watery surface and oxygen-rich atmosphere are unique among the planets, and they support an incredible diversity of life. The Moon, in contrast, is stark and lifeless. This spectacular interloper from the farthest reaches of the solar system is a comet, a mass of rock and ice. Near the Sun, the ice evaporates to form a tail millions of kilometers long. Venus is Earth's closest neighbor and is similar in size, but its dense atmosphere of carbon dioxide traps sunlight, making the surface hot enough to melt lead. Airless and heavily cratered, tiny Mercury endures temperatures that rise to 400 degrees Celsius during its day and plunge to minus 170 degrees Celsius at night. At the center of our solar system is its most important member, the Sun, a small star only about halfway through its very long life. Beyond the solar system, other planetary systems are forming around distant stars. Perhaps one day we'll learn whether any of them resembles our own.
Hi, we're back in the Meteorite Gallery. I'm here with Dr. Bob Sullivan. Bob, you want to tell our viewers who you are and what you got there in your hands?
Well, I'm the Associate Director for Public Programs here, and Glenn, I'm glad to be here with you, a world's expert on meteorites, because I'm sure I've got something very important. This came through my window the other night, and it's round, and it looks metal, and like it's traveled a long way, so tell me I've got an important meteorite on my hands.
Well, that's a really neat looking specimen, Bob. In fact, I haven't seen one like it before, but I hate to tell you, it's not a meteorite. And so it makes me wonder, have you been chasing the neighborhood kids off your lawn for playing baseball again?
Oh, that could be it. That could
Well,
definitely be it.
But if it's any consolation, this is a very interesting rock. It's unusual. It's actually a piece of slag. This is formed when they have two scoops that they reach into the blast furnace to get a sample of slag out of, and it forms this ring around the outside. But what it doesn't have, Bob, is a characteristic that all meteorites have, which is when they come through the atmosphere, they get heated up, and they melt on the outside, and they get a black, glassy crust on the outside, which this doesn't have. So I'm sorry, but this isn't a meteorite.
What a
but it's a
disappointment.
neat specimen. I
Well,
suggest you throw it back at him.
Yeah, this one maybe have been chucked through my window by a nasty neighborhood kid, but how would you know that a meteorite was like this, and how would you know where it came from, Glenn? How would you figure that out?
Well, we know that most meteorites come from the asteroid belt, and the way we know that is because we've actually had a chance to photograph several of them as they come into the atmosphere, and it gives us a chance to triangulate their path. And a few years ago, back in 1991, a very large meteorite was seen on a Friday night when a bunch of people were at football games with their camcorders photographing the football game, and we're actually able to record it in enough detail to show where it came from. And the tape that you're about to see is going to show you how this meteorite came from the asteroid belt.
Let's take a look.
Friday evening, October 9th, 1992. Fans at high school football games along the East Coast look up and see something amazing. A brilliant fireball blazing across the night sky. Traveling northeast, the fireball comes in so low that at least 14 people in 8 states capture it on videotape, 4 of which you see here. What they witnessed was the fiery passage of a meteorite that broke into many pieces before it hit the ground. Only a single fragment was ever recovered. It landed near Peekskill, New York, smashing into the trunk of a parked car. Now watch again. The direction in which the fireball appears to travel looks different in each video because of the different camera locations. Live recordings of the meteorite showed that it was going 50,000 kilometers per hour when it hit the atmosphere. Comparison of the tapes also revealed the angle of the meteorite's descent toward Earth. Knowing the meteorite's speed and trajectory, scientists retraced its path back through the solar system and discovered that it came from the asteroid belt, a zone of rocky rubble between the orbits of Jupiter and Mars. For more than a century, people have wondered where meteorites come from. With the Peekskill videos and still photos recording the descent of several other meteorites, now we know.
Hi, we're back in the gallery, and I'm here with Dr. Timothy McCoy, who is my colleague as meteorite curator here in the Department of Mineral Sciences. And we also have with us Ileana, who's a student from T.C. Williams High School in Alexandria, Virginia. And we're here with some meteorites sitting here, and we wanted to show you a little bit about the variety of meteorites that we find and a little bit about what they tell us. And this particular meteorite here, which has the name Goose Lake, is certainly our largest and one of our most famous meteorites. Tim, tell us a little bit about this meteorite and how did it get that name?
Well, this is the Goose Lake meteorite, and meteorites are named for the places they come from. This one happened to come from Goose Lake, California, and it's a fairly unusual meteorite in that it's so large and that it's made out of all metal. Iron and nickel are the main components of this meteorite. Now, this is what most people think meteorites are, great big chunks of metal. But in fact, as I say, this is pretty unusual. In fact, this meteorite is so unusual because it has this very rounded shape compared to a lot of others that we'll look at. And that's because this was found on a lava flow in California. It may have actually been engulfed in that lava flow. But like I say, this is unusual. Most of the meteorites we find are much, much smaller. And that's what we're going to take a look at. Some of these different kinds of meteorites, where they come from in space, and what they're made of. And we're going to return to a lot of these later, so you want to keep some of these in mind. Glenn, why don't you tell us about these first two?
What I have here is a slice. This has been cut with a saw of a type of the most common meteorite that we actually have falling on Earth. It's called a chondrite. And this is made entirely of rocky minerals, very similar to minerals that we see in rocks here on Earth. And this rock is actually a very interesting one because it's an aggregate of many different types of grains. And this is 4.5 billion years old, as are most meteorites. Yet a different type of rocky meteorite, and this is one of our most famous meteorites. In fact, it is our most famous meteorite. This actually formed by the solidification of molten rock, so it's called an achondrite. And this particular rock comes from Mars. And this is very famous because this is the rock that a year and a half ago, some scientists from NASA's Johnson Space Center think they found evidence for ancient life on Mars inside of it. Tim, what are these other two meteorites that you have sitting here?
Okay, well, I've got a couple of others. The meteorites that you showed, one is called Allende, came from Mexico, and this meteorite came from Antarctica. Well, this meteorite also came from Antarctica. It's called Teal Mountains, and it's a palisite. It's something we would call a stony iron because it's made of some silicate material, some rock, which is the green stuff called olivine, and some metal, the shiny silver stuff, which I think you can see there. And this rock, too, came from an asteroid. Most meteorites do come from asteroids. Relatively few come from Mars. And we'll show you how this formed in a little bit. Now, while they're not the most unusual kind that fall to Earth are irons, they're among the most common kind that are found. Why do you think that is, Ileana? Why don't you hold that for me?
It's very heavy.
It's extremely heavy. And if a farmer found this in his field, he'd realize right away this was no ordinary rock. And they become even more extraordinary if you cut one open. This is the Gibeon meteorite found in South Africa. And when you cut it open, you come to this very unusual pattern. This is made of iron and nickel metal. And we're going to show you how this formed in a little bit. How do you think we know all this about meteorites, Ileana?
Well, I really don't know.
Well, our job isn't just to collect meteorites or to distribute meteorites to scientists. It's also to learn a lot about meteorites. And not only meteorites that we know are meteorites, that we already have in our collections that we're studying, but new things that come into our collection. And so why don't we go behind the scenes with some of your classmates to follow the journey of 3 rocks that came to the Smithsonian and learn about how we study these and how we actually learn about the genesis of these rocks 4.5 billion years ago. So let's follow that journey of a rock, Ileana. Okay, well, we've come behind the scenes with Aaron, Joe, and Julie to try to follow some rocks from the time they come into the Smithsonian to the time we actually learn something about them, about their formation, about how we learn about the journey of a rock, the history of a rock. And we're going to follow these 3 rocks, and these are the kind of things that we get sent in all the time. This came in a couple of weeks ago. It's kind of shiny and silvery, and someone thought this was a meteorite. What do you think of that rock, Joe?
Kind of heavy.
Yeah. What do you think, Aaron? Is it as heavy as the iron meteorites we've gotten?
Not really, no. It's kind of heavy, but not that heavy.
No. In fact, this isn't a meteorite. This is a piece of metallic silicon. This is the kind of stuff we'd make computer microchips out of. And so I don't think we need to follow it much more. Sometimes we get rocks like this. You can see the outside is kind of black looking, like maybe it burnt when it came through the atmosphere, and the inside is different. That's sort of promising looking. What do you think of that rock?
Nice. It kind of looks like one.
Yeah?
Materials in it.
Yeah, well, it might be. So let's think about taking that rock a little further on our journey. And finally, this is something that came in from Ohio a couple of weeks ago. It doesn't have any real distinguishing features, except that it's kind of a heavy rock. And so maybe that's the kind of thing that would be a stone meteorite. So maybe it's worth taking that further on our journey. So why don't we go downstairs to the next step, where we actually see how we unravel the history of one of these rocks. What we really want to look at is the inside of these rocks. So we're going to cut a piece off to see what the inside of one of these rocks looks like. You mind taking a piece off that for me, Tim?
No problem.
All right. Yeah.
Something like that?
Yeah, that'd be great.
Okay.
So Tim's going to use this water-cooled saw. It has a diamond-impregnated blade, and the diamonds basically abrade away the material. We use a lot of water because we both want to cool the saw and the sample, and we want to carry away the bits of rocks. You can see a blade like that goes through a rock pretty quickly, and you can see the water dripping down because we're pumping huge amounts of water into the process. I mean, in the last few seconds, we're already basically halfway through this rock. And so this allows us to look at the inside. More water still dripping down. And there, now we've got a slice off of the rock. And so if we look at the slice of the rock, if we dry it off here a little bit, and Aaron, Joe, and Julie can look at this, it's not kind of disappointing because what you see is that the inside doesn't really look all that different from the outside, and that's not a very good sign for a meteorite. If this were a real meteorite, the inside would look quite different. And so I think this is where the journey of this rock ends right now, because this obviously isn't a meteorite. So let's continue with this rock, which remember has this outer bubbly surface, and let's see what it looks like on the inside. Do you think you could take a piece of that off for us, Tim?
Sure thing.
All right, thanks a lot.
Okay.
Well, we're back with Aaron, Joe, and Julie upstairs in another of our sample prep labs. And we've got the piece of the rock that was cut open. And you can see it's pretty coarse grained. Nice big minerals in there that we can see. But we want to learn what these minerals actually are. So what we're going to make is one of these. This is a polished thin section, a very thin slice of the rock attached to a piece of glass. How do we go about making one of these? Well, you start with a little square of the rock, like this, and a plain glass slide. And you just glue those together. And then you might cut away most of this material. But then once you do that, you take the glass slide and you put it down on here. There's one underneath this brass piece. And you just let it go around and around and around with grit that you put on here that grinds away most of the material. And you start with a fairly coarse grit so that you get most of it off, and you just work finer and finer and finer until the final product is as smooth as a piece of glass. And this is only about 30 microns thick. How thick do you think that really is?
Really thin.
Like, what do you think compared to a piece of paper?
Probably like half a piece of paper.
That's right. It's about half the thickness of a piece of paper, and the light will actually shine through it. So using a polished thin section, we can actually identify the individual minerals that make up this rock. So let's go over to the microscope and do that. Well, we've got the thin section in the microscope now, so hopefully we can learn what the minerals in this rock are. So what do you think you're seeing here on the TV screen?
The minerals, I guess. Why are they different colors?
Well, what we have is a polarizing microscope. And it takes, light is made of waves, which come in many different directions. And this is capable of selecting certain waves that are given off by the minerals. And by looking at the colors of the minerals, you can see some are very brightly colored, this purple, and others are pretty dull colored. And by looking at the patterns and the colors, we can learn what the minerals are. In this case, we have olivine and pyroxene, and this is plagioclase in here. Well, we're in luck so far because these are the same minerals we find in meteorites. So it's still possible that we have a meteorite here. What we need to know now is, what are the compositions of these minerals? So we need to go to another piece of equipment, and that's where the journey of our rock will finally end. Well, this is the instrument we're actually going to use to learn the chemical compositions of the minerals in our thin section. This has a fancy name. It's called an electron probe X-ray microanalyzer. And basically, the name says it all. Electrons are because we're bombarding the sample with a stream of electrons. And that's what we're looking at here. This image is generated by measuring the electrons that are hitting the different minerals and how they react to that electron bombardment. When we hit the sample with electrons, it gives off X-rays. And what this device allows us to do is to measure how many X-rays are given off and to learn the chemical composition of individual points, micron-sized points. That's why we call it a microanalyzer. A micron's about 1,000th of a millimeter. So we're looking at tiny little spots within individual mineral grains. And we've done that with the thin section we had before, and, well, there's bad news. It's not a meteorite. The chemical compositions aren't like those of meteorites. But I think you've learned a lot about how we learn about rocks and how we recognize meteorites. So we're going to throw it back to Glenn, who's going to take some of your classmates and put them to the test on whether they can recognize meteorites from meteorons. So back to you, Glenn.
Thanks, Tim. I'm here with JC from TC Williams. That's a pretty sophisticated way of learning whether it's a meteorite or not, Tim, and that's an amazing piece of equipment, actually. But maybe that there is an easier way that people can use at home to recognize whether a rock might be a meteorite or not before we actually go to the effort of putting it in that electron microprobe. I've got JC here, and we're going to look at a few rocks and see if, how well JC has done his homework about learning how to recognize a meteorite. But while the rest of you are watching, you may want to call in with questions. There's a number that should be on the screen. It's 1-800-566-1115. If you have questions while we're going through this, feel free to call in. So JC, we've got 6 rocks here. And this is our little quiz for our visitors who come to our meteorite gallery to see if they can learn how they recognize a meteorite. So for example, rock number 3 sitting over here. Do you think that that's a meteorite?
Yeah, I think it's a meteorite because it has little iron particles in it. And if you look at the outside, it's totally different from what's inside. It's the fusion crust, right?
What is that fusion crust from?
It's from when it enters the atmosphere and it melts together and it's like compacted.
Wow, well, you've really been doing your homework. Okay, let's see if I can find a harder one. Well, what about number 5 down there? Do you think that's a meteorite?
Yeah, it's the crust looks like a fusion crust. It looks like it's been through some wear and tear when it enters the atmosphere.
Well, why don't you push the button and see if you're right? It is a meteorite. We've got a phone call coming in. Hello? Hello? I'm here. Sir.
Hello?
What's your question?
Yes, I was just wondering if the scientists ever got an element in the meteorite that they have not ever seen before, like a strange new element.
No, the laws of chemistry and physics don't change just because we leave the surface of our planet. The elements are the same, and in fact, even most of the minerals are the same. We have found some minerals in meteorites that we don't see in rocks on Earth, but that's because they form under very special conditions. But we can actually duplicate those minerals. We can make them synthetically in the laboratory. So let's go back to JC here, and let's give him one last test and see, what do you think number 1 is, JC?
Number 1, I would say, is an earth rock.
And why do you think that it's an earth rock?
It's round. It doesn't look like it's gone through the wear and tear of entering the atmosphere. And the little crystals look plain and something you'd see.
Well, try to take the test and see whether you're right. You're right. It's an earth rock. It doesn't have the fusion crust, and it doesn't have metal. So that rock fails the test, but you passed yours with flying colors. We have another phone call in from Catherine, I believe. Yes, what's your question?
How come you won't touch the meteorites with your hands without gloves on?
That's a very good question, because your hand has salt and oil in it, and if we touch the meteorite, it contaminates the meteorite. Some of the studies that scientists do on meteorite involve very, very tiny amounts of material from the meteorite, and the material that's in your hand, the oil and the salt, would completely contaminate the results. So we try never to touch the meteorites with our hands. Also, meteorites contain metal, and the oils in your finger and the salt in your finger can corrode the metal, and we don't want to do that either. We have another phone call. William from Virginia, what's your question?
I wanted to know why is a meteor different than a meteorite?
Well, a meteor is the name we just sort of use somewhat humorously to refer to rocks that get sent into us for identification that turn out not to be meteorites. So meteorons are not meteorites. They're just Earth rocks that look strange, and people wonder if they are meteorites. But a meteorite is actually a piece of another world that falls from outer space onto our Earth, and those are what we study. So back to Serena for more question and answers.
Okay, I just want to call your attention again to our web page where you can connect to such links as the Meteoritical Society, which has pictures of meteorites and a lot of useful information that will reinforce what we're talking about today. I want to also apologize for that 1-800 number, which was incorrect when I read it to you last time. I hope I get it right this time. 1-800-566-1115, or try our web page or fax. Do we have any questions coming up? On email? On phone? How about Stark County? Do you have any questions?
Yeah, I want to know, how can you tell how fast the Peekskill meteorite was going? How do you know it's going 50,000 kilometers an hour?
Oh, that's a very good question. I'll just repeat it, Glenn, so that you can hear it. How do you know that the Peekskill meteorite was going how many thousands of kilometers an hour it was going when it hit the Earth's surface or the Earth's atmosphere? Glenn?
Well, it turns out that we actually had video films of it. I think, as I mentioned earlier, when the meteorite fell, it was at nighttime when a lot of people were watching football games out at stadiums and high schools all over the East Coast. And people with their video recorders saw this very bright meteor shooting across the sky, and they took their cameras up and photographed it as it fell. And by using those videos, we can reconstruct the actual speed of the meteorite because we've got it on film. And it shows how fast it was going, which was about 20,000 miles an hour.
Glenn, I understand we have a question from Carl from Indiana. Go ahead, Carl.
Yes. Do meteorites have metals that have never been found on planet Earth before?
Do meteorites have names that have never been found on planet Earth before?
In them that have never been found on Earth.
Oh, do they have metals that have never been found on planet Earth before? Tim, I'd like to field that question to you. Do meteorites contain metals that have never been found on planet Earth before?
Well, as Glenn said, sometimes we find minerals, and metals are basically minerals, combinations of elements that are not commonly found on Earth, things like iron carbides or some iron silicides, but we don't find elements that aren't found on Earth. And these special combinations are probably because most of these rocks that have the special minerals formed where there wasn't much oxygen. On Earth, there's lots of oxygen. In some meteorite parent bodies in these asteroids, there wasn't much oxygen. So we do find different minerals, including metals, but not different elements.
Okay. Now that we know what meteorites are made of, it's time to figure out a little bit some of the stories that meteorites can tell us. I think that's your province, Glenn. What kind of stories can meteorites tell us?
Well, as you may have seen earlier when Tim and I showed you some of the sampling of meteorite specimens, you may have noticed that there's a great variety. There are stony meteorites, there are rocky meteorites, and within each of those there's a huge variety of properties, and each of them tells a different history. If you put all those meteorite histories together, what they're telling us is the history of the solid bodies in the solar system. They're telling how planets first formed and then evolved to their present form. I'm standing here next to a graphic in our exhibit hall, and this illustrates, it's a timeline that shows what we can learn by studying meteorites from the time when the solar system was just a disk of gas and dust in orbit around what would eventually become the sun, through the formation by sticking together of tiny grains to form essentially cosmic dust balls, and the sticking together of those to form larger and larger rocks, eventually to the point where you start getting asteroid, moon, and even planetary-sized bodies that get very hot on the inside and actually melt to form cores and mantles and crusts. But it's possible, actually, in some rare meteorites to go back even farther than that. We have in our collection a meteorite which I'm going to show you now, which actually has history recorded in it from before the solar system ever formed. And this is one of our most spectacular meteorites. If you'll come with me, Over here, we have a piece of a meteorite that fell in 1969 called the Allende meteorite, which we showed you another piece of earlier. And if you take a piece of the Allende meteorite and dissolve it so that all of the minerals and everything have dissolved away, it turns out that you don't quite dissolve everything. And what's left behind is a small amount of tiny white powder, which you see on the screen in front of you. At the very bottom of that vial is a powder that consists of tiny crystals of diamond. And those diamonds actually formed before our solar system formed. Those diamonds formed in the explosion of a dying star, a supernova. They were expelled from the star as it exploded out into space and eventually became part of the matter that went into our solar system. So we actually have material that goes from before our solar system formed. But now we're looking at the same meteorite, Allende. We had a chance earlier today with some of our friends from T.C. Williams to go back behind the scenes into the main meteorite collection and look at some of these meteorites, which we call chondrites, and learn how they tell us about the earliest history and formation of the planets. So let's go back to that tape and see how these meteorites tell us about.
We talked out in the hall about the fact that planets and asteroids formed from accretion of small bodies early in the solar system. Well, Patty and Ben and Adam here are a little bit curious about how we know how that happened, about what the evidence is for how the planets formed. So we've come back to the main part of the collection in the meteorite room to look at some specimens to get some idea of what we look at that gives us the idea that planets formed from small pieces of material. When you look at a rock like this, what do you see? Would you be interested in knowing that this rock is 4.5 billion years old? When you see this, what do you see in detail when you look at the surface of this rock?
It looks kind of like concrete. There's all sorts of things, different things stuck together in it.
Well, in fact, that's exactly right. Every single grain in this rock, and this is a meteorite, which you can tell, among other things, because it has the black fusion crust on the outer surface, and this is a piece of a large meteorite. These are all pieces of the same rock. Every one of these particles is 4.5 billion years old. The whole rock is 4.5 billion years old. And this meteorite came from the asteroid belt. And the grains, all of the grains that are in this rock originally were bits of dust and matter, sand-sized pieces of matter drifting in the solar system before the planets existed as planets, before the sun even existed as a sun. When our solar system was just a cloud of gas and dust in a disk-shaped configuration, slowly rotating.
Wait, if all the material in the solar system was homogeneous, how can you have different kinds of meteors? I mean, were there clumps of particles that...
Well, it wasn't completely homogeneous, but keep in mind also that we do have some meteorites that are fragments of larger bodies that did evolve to melt on the inside. So we have some meteorites that represent asteroids that had cores and mantles and even volcanic eruptions on the surface. So we have volcanic rocks. We have meteorites that consist, like this one, of nickel iron metal, which comes from the cores of these asteroids that were formed and destroyed, as it turns out, long ago. So much of the diversity that you see, the most prominent diversity reflects the fact that not all meteorites are chondrites like this one, which is this dust, but some of them represent more evolved, larger bodies, planetary and moon and asteroidal-sized bodies.
How big this meteorite was before it came down to Earth?
This is actually a very special meteorite. And that's a great question, by the way. All four of these pieces are from a single meteorite that fell in 1969 in the desert in northern Mexico over a little pueblo, a town called Allende. And thousands of these fragments rained down. The fireball came in at night and exploded high in the atmosphere and showered down these fragments, and it lit up the entire night sky over southwestern United States and northern Mexico. And because the fragments fell in the desert, they were very easy to recognize. There isn't a whole lot else there in the way of rock. And so these large, even though these are very large, when they landed on the ground, they just kind of landed with a plop. They didn't bury themselves. And we estimate that the total amount of material that was recovered, that we actually picked up off the ground, was in excess of 2 tons. And since these, you notice the fusion crust on these, when these things came into the atmosphere, they started to melt and a large amount of material was actually lost. So the original meteorite may have been 50% larger than that in mass, and that extra 50% was lost during atmospheric entry. Well, now I'll turn it back to Tim, who's out in the hall, and who's going to tell you more about how these meteorites tell us about how planets evolved after they had accreted from the dust. Tim, to you.
Thanks, Glenn. I'm here with my friend Sarah, and we're going to talk about what happened once asteroids melted. And not surprisingly, in the chondrites you looked at with Glenn, there were a lot of different components with different densities. And when they melted, all the heavy stuff sank to the middle to form a core, and the light stuff, the scum, rose to the surface to form the crust, and in between you had a mantle. And if you have any questions about what we've been talking about so far, I'd encourage you to call in. The number is 1-800-566-1115, and we're going to actually look at these layers of these differentiated worlds. Well, the first layer is this crust, this scum of material. And this formed when molten rock welled up from the inside of the asteroid and erupted on the surface. If I could have the first picture. This is a lava flow in Hawaii. This is from the Kamoamoa Black Sand Beach. It's a Pohoihoi flow. And this is molten rock that welled up from the inside of the Earth and erupted in Hawaii. Well, the same process happened within a few million years of the formation of asteroids. If we can have the next picture. And this is an artist's conception of volcanoes on other worlds in the early history of the solar system. Okay, we have a phone call. Why don't we go to that? Brian, you have a question?
Yes, I was just wondering if you had any cases of meteorites coming through the Earth and hitting people or injuring anybody or anything?
Well, the question is, do meteorites ever come through and hit people or injure anything? Well, quite a few meteorites have actually been recovered that have landed in various houses. One did hit a lady in the 1950s. And in fact, one of these meteorites that we're holding here, Peña Blanca Springs, landed in a swimming pool. It was observed by many people, and then they went out and recovered it. So let's go back to looking at these two rocks with Sarah. What do you think the difference between these rocks are, Sarah? I mean, we've talked about volcanoes on other worlds. Why don't we just have one rock and say this formed on a volcano on other worlds?
I think they're probably made of different things, different compositions.
Yeah, they are made of different compositions, and there are a lot of differences in the details of how these rocks formed. But the most amazing thing is that these formed on two different ancient worlds, two asteroids, probably millions of miles apart. But because of the history they've been through, you can hold them here only 3 inches apart. So these are from two different worlds. But we can actually go down into the core of another world. So I'm going to go talk to Kirsten, and we're going to look at the inside of an ancient world. Okay, we're over here with Kirsten, and she's holding in her hand a palisite. What do you think of that rock? Kind of pretty, isn't it?
Yeah.
Yeah, these are among our most beautiful rocks, and these are the stony iron meteorites, mixtures of olivine, the silicate mineral, and iron nickel metal. Where do you think something like this formed?
Well, maybe it mixed because two different asteroids collided and different layers.
Well, that's a possibility. These are probably, the materials are from the same planet, but there probably was mixing. And that mixing, if you can see the image here in the back of the case, was at the core mantle boundary. The mantle is mostly olivine, the core is mostly metal, and just like a raft sinks down into water, the olivine-rich mantle probably sank down into the core and mixed these two components. So here we're looking at the inside of an ancient world. But we can go even deeper down, if you want to hold on to this, into the actual cores of ancient worlds. And those are represented by iron meteorites. And you can see here we have a whole case of iron meteorites. How many different worlds do you think are represented in this case, Kirsten?
I'd say maybe about 10.
That's a really good guess. There are actually 11 different worlds in this one case, as many as there are in almost the entire rest of the exhibit. And you can see they're enormously different in the kind of textures that they have and patterns. And that's for two reasons. First of all, each different world had a different chemistry, and chemistry controlled a lot of how they formed. But they also have different cooling histories. Some cooled very slowly and got a very coarse texture in them. The crystals had a long time to grow. And others, like the Gibeon meteorite that we looked at before, has a very fine texture. It didn't have very long to grow, but it also has a different chemistry than these. And some, if we go down to the far end of the case here, Kirsten, if you want to take a look, actually have silicates within them. Chunks of the crust, believe it or not, of this world that were mixed down into the core somehow. Well, the most striking feature is this thing. We call it a Widmanstätten pattern. And it tells us a lot about how this meteorite actually formed, the Gibeon meteorite. And we have a video that shows you the formation of the Gibeon meteorite. So let's take a look at that video.
The beautiful pattern on the Gibeon meteorite could never have formed on the surface of the Earth. Why? The pattern, known as a Widmanstätten structure, appears only in metal that cooled slowly, perhaps by a degree or two every million years. This could happen only in the well-insulated core of an asteroid or planet. Gibeon formed billions of years ago in an ancient world. Molten at first, the asteroid's nickel-iron core gradually solidified as it cooled. Even after it was solid, the core continued to cool slowly. So slowly, in fact, that the atoms separated into two different metals. The bands you see are the iron-rich metal. The areas in between are rich in nickel. Long after the pattern formed, another body crashed into the asteroid and sent chunks of the core flying into space. Billions of years later, a fragment plunged through Earth's atmosphere, broke apart, and showered pieces over what is now the country of Namibia. In 1912, one of those pieces came to the Smithsonian, where the long process of unraveling Gibeon's early history began. For this exhibit, a Smithsonian preparator cut the meteorite open with an abrasive saw, and then ground the surface to remove the saw marks. Finally, he gently bathed it in nitric acid and alcohol. Because the two metals dissolve at different rates, the acid bath revealed the crystal structure for the first time since it formed on another world billions of years ago.
I understand we have a question from Daniel of Indiana. Daniel, are you there?
Yeah.
What's your question?
How do you know how old a meteorite is?
How do you know how old a meteorite is? Well, meteorites are rocks, and we know the same way we know for rocks. Certain minerals in the rocks contain radioactive elements that decay over time. By measuring the concentration of the parent that's decaying to a daughter atom, we can tell exactly when the minerals in that rock crystallized. And that's how we measure the age of all rocks, not just meteorites. We have a question from John of Massachusetts. John, what's your question?
Yes, I work at the Oak Grove Cemetery in Springfield.
Yes.
And I was out there doing some landscaping, and I found an iron-nickel meteorite.
You found an iron-nickel meteorite in Massachusetts.
Kind of a nugget.
An iron-nickel nugget. How do you know it's a meteorite?
Well, it's rusty.
Uh-huh.
And tiny little thumbprints in it.
Tiny little thumbprints in it. Well, if you want to have your meteorite looked at by a meteorite expert, you can send it here to the Smithsonian or to a university to have it tested to see if it really is a meteorite.
Uh-huh.
Okay, we're going to have to move. We're going to have to go to Stark County. Go to Stark County for a question. Do we have some questions, Stark County?
Yes.
Hi.
What was being removed by the alcohol and nitric acid?
what was being removed by the alcohol and nitric acid? It was etching the metal preferentially. There are two kinds of metal in those meteorites, and one etches preferentially in nitric acid. That brought out the texture. Kelsey from Indiana, you're on the air. What is your question?
About how many different metals are found in meteorites?
How many different metals are found in meteorites? I'm going to refer that to Tim. Tim, how many different metals are found in meteorites?
Well, that's a really good question. Dominantly, really, there are only two metals. One we call camosite, which is relatively poor in nickel, and one which we call taenite, which is relatively rich in nickel. The bands you see are the camosite. The intermediate stuff is the taenite. And there are a few other exotic metals, but they're found in such small abundances that you probably couldn't even see them in a piece like this. But that's a really good question.
Okay, we've gone from talking about the metals in meteorites and looking at their deep interiors, but now we need to know how did the asteroids and planets come to be? Now that we know their anatomy, we need to know their origin. Tim, can you tell us something about that?
Well, Glenn talked a little bit about how we make a planet. Tiny dust grains start to stick together. They build larger and larger objects, which eventually form asteroids, and those asteroids start to heat up and melt, and you form a core and a mantle and a crust. But hopefully what you picked up in that last video is that there's another process that's extremely important in all of this, and that process is impact. If it weren't for two asteroids colliding, we wouldn't have any meteorites in our collection today, because those asteroid collisions are what start things on their path to Earth. So let's go to Glenn, who's going to tell us a little bit about the smallest scale of impacts, and we'll move up to the largest scale of impacts.
Hi, I'm back here with JC, and we also have our old friend, the Allende meteorite, which you've now seen a couple of times earlier today. JC, you want to take this meteorite, tell me what you see in there, and describe it.
I see like many sized particles. I see like little black ones and gray ones, and I see big white particles in it.
And how do you think such a rock formed?
They probably all like got crushed together.
But if you look at them, a lot of them are almost perfectly round. A lot of the smaller ones are perfectly round. So do you think that when these things crashed together, they were really crashing together at high speeds and destroying each other, or what?
Probably not, since they retain their shape so well.
That's exactly right. What we're seeing, this rock, when we look at this rock, we're actually seeing the process by which things first started to form in the solar system. And we're actually studying the process by how those grains come together. And what we're seeing, as JC correctly pointed out, is that unlike when we usually think of collisions as being very, very violent things, with large things coming together at high speeds and destroying each other, when the solar system first formed, we had small little grains of dust come together at relatively gentle speeds, and they were just sticking together. And this process, which is the beginning of the process by which the planets formed, is called accretion. And by studying meteorites like Allende, we see that this first process, this is a variety of impacts. These are little things, though. The impacts are very gentle, and they're sticking together to form larger and larger bodies, or rocks, like this one. But now Tim and Claire are going to tell us about impacts as they get more evolved, as planets get more evolved, and the impacts get more violent. So Tim and Claire, it's over to you.
Okay. I'm here with Claire, and as Glenn said, meteorites, as collisions started to happen later in the solar system, they got more and more violent, and they formed impact craters and all sorts of geologic, and as I'll show you in a minute, biologic effects on the evolution of the Earth. And the Earth, of course, was not protected, but meteorite craters are relatively rare on Earth because wind and water and erosion diminish them with time. This is probably one of the most famous meteorite craters, if you can see it in the back. That's Meteor Crater in Arizona near Flagstaff. How large do you think that crater is, Claire?
It looks like it's about a mile across.
That's right. This is about 3/4 a mile across, and it's a relatively young crater, so it's well preserved. And this is what a classic simple-shaped crater looks like. But we can also study other kinds of things from craters. Many times we actually recover meteorites from craters. This is called the Canyon Diablo meteorite. It's named for a little stream that runs near Meteor Crater. And this is a piece of the impactor that actually made Meteor Crater. We can also study rocks from the bottom of Meteor Crater. This was, well, it still is a piece of sandstone, but it's a very different kind of sandstone. Why don't you hold on to that, Claire? What do you think of that rock?
It's really light. It's
A lot lighter than sandstone normally is.
That's right. It's much lighter. It's more like a piece of pumice. Many of you have had a piece of pumice in your hand, and this is what happens when rocks are shocked on Earth. They're compressed, and then as they decompress, you get little bubbles in them, and all sorts of changes take place to the rock. So, enormous geologic implications. Okay, I'm going to leave this rock with Claire, and we're going to go up in scale, and we'll look at a series of photos that track from Sikhote-Alin, which is a relatively small crater, only a few tens of meters across, up to Manickawagan, a crater about 100 kilometers, about 60 miles across. But the real granddaddy of craters on Earth is called Chicxulub. This is the Chicxulub crater. It's found in the Yucatan Peninsula of Mexico, and it's about 200 kilometers across. Now, Marie here was holding this rock, and actually, let me turn the rock over here. What do you think you're holding? What do you think you were holding here, Marie?
A rock inside another rock.
Well, it's a rock, and we put it in this plaster cast because it's pretty friable. It'll break apart. But what this really is a piece of time. It's not so much a rock, but you're actually holding time in your hands. And the time here is 65 million years ago. And 65 million years ago, if you look at rocks from all over the Earth, you find a little layer like this. And that layer is rich in an element called iridium, which is common in meteorites but rare on Earth. And the presence of that iridium caused some scientists a few years back to think, now you have this global layer of an iridium-rich clay. So maybe there was some catastrophic event, and they started looking for a crater, and it took them almost 10 years to find the Chicxulub crater. But when they did, they became convinced that this was the crater, this was the impact event that caused the extinction of the dinosaurs 65 million years ago. So you're actually holding in your hand here the rock that formed when dinosaurs went extinct. And we have a whole video that shows this process taking place, and we want to show that to you now. So let's go to the video.
Gazing down on our planet today, we see a serene blue world. But 65 million years ago, when Earth looked much like this, an asteroid the size of Washington, D.C. shot in from the southeast. Going more than 11 kilometers per second, it blasted through the atmosphere and struck Earth with such force that it punched a hole nearly through the crust. Shock waves expanded into a giant dome, and a fountain of hot debris sprayed into and even above the atmosphere. Mountain-sized blocks splashed down near the crater. Smaller fragments traveled thousands of kilometers, and finer particles encircled the globe. Wildfires spontaneously ignited across much of the Earth. At the same time, a giant wave, a tsunami, raced toward the coastline, growing into a kilometer-high wall of water before it swept across Central America and penetrated deep into North America. Plumes of ash and smoke from the wildfires filled the skies, creating a giant cloud that cloaked the Earth in darkness. The crater that was left stretched more than 170 kilometers across. As inrushing water swept over its superheated rocks, clouds of steam drifted across the ocean. Within 1,000 kilometers of the crater, the retreating tsunami scoured the land there. Dust and soot that filled the atmosphere may have blocked sunlight for more than a year, setting in motion a chain of events that destroyed as much as 70% of all species, including the dinosaurs. But the mass extinction also created opportunities for the survivors. Many small mammals escaped this catastrophe and began to flourish. For the Earth itself, the collision was only one among many impacts that formed and are still reshaping our planet.
The Chicxulub impact was an event of almost unbelievable violence and unimaginable violence. There's nothing in human history to give us any sense of the scale of such a global catastrophe. And yet, as huge as that event was, we have evidence that early in the solar system's history, when the Earth was still very, very young, and the other planets were very, very young, even more violent events were taking place. In fact, the most violent event we know of caused the formation of Earth's moon. Standing next to me here is a graphic that shows that we think that about 4.5 billion years ago, shortly after Earth had just formed, imagine a planet the size of Mars hitting Earth, and in the process, destroying itself itself and ripping away about a third of Earth's material. And that material then went into orbit around the Earth. This molten and red-hot vapor went into orbit around the Earth and eventually congealing to form Earth's moon. And shortly after they'd formed, both Earth and moon at that point were completely molten. And yet, as violent as this event was, after the moon had formed, the violence didn't end. Impacts continued and have continued throughout Earth's history. If you come with me, I'll show you that there's evidence preserved on the moon for even more events taking place after it had formed. We have evidence that the moon continued to be pummeled by gigantic bodies the size of asteroids hitting it and forming and continually reforming the rocks on the moon's surface, such as this rock here, which is what we call a breccia. It's a rock that's made up of fragments of rocks that through continuous impacts have been broken up and reformed. Now we're going to go back to Serena, who is in activity to show you the relationship between the size of objects as they hit and the speed and how that affects the violence and how it controls the process that we called impacts. Serena, to you.
Okay, now comes my favorite part of the program, make your own crater. Are you there, Stark County? Because we're going to be doing this across country. Stark County, are your experiments set up? You ready to do your cratering? Yeah. Okay, ready to go? And Tim McCoy is going to be across the room doing some cratering experiments with the T.C. Williams crowd. Tim is there. Yeah. Okay, I'm here. Now we're going to make some craters. All right, let's start this way. We're going to take a golf ball and drop it 3 times into the pan. Go. 1. Whoa, great crater. Okay, let's do it. 2. Wham. Oh, super. And 3. Okay, we've now done 3 different craters, 3 craters from the same object at different times. Now we're going to put another set of craters from a different object on top of those 3. Okay, ready? Aim. Wow! Oh boy, that one really does a good job. Okay, that's 1. And let her go. 2. Oh! And 3. Okay. Super. Now let's look at the results. What we've taken is a very nice pan that originally had a blue top layer and a white underlayer, and we've made it a real mess. But you can see, except for my fingerprints where I took these things out, that there are what we call overprinting relationships. This crater's all by itself, but it's put out rays. Do you see them? Of flour that have been dispersed onto our soil. And those rays are just like the debris that are ejected during an event where during a cratering event. You see, this one's all by itself, but its rays are overprinted by this one. And then finally, the best circle of the golf ball is here. Okay, Tim, what are your results?
Well, we've managed to make a horrible mess over here, but the T.C. Williams students have found pretty much the same thing, that we have the first impact crater, which was here, has rays around it, which are then broken by the second and third craters. But interestingly, this is the same kind of thing you see on the moon. If you look at a map of the moon here, for example, you see this crater made rays that come out from here, and this crater cuts those rays. So this formed later than that. And the use...
I think we need to go to Stark County and find out what they discovered. Stark County?
Yeah.
What have you got? Wow, great rays, guys.
Oh, yeah.
Okay, we dropped 3 marbles, and you can see here that this one was more recent because of the ejectives covering everything else.
Uh-huh.
And that this one here was the second one dropped because there's debris in it.
Right.
And you can see that the first one here is covered up because there's almost no crater and all the ejectives out to the side.
Super. And before we move back to Glenn, I just want to show a quick view from the web page of the surface of the planet Mercury. This is a real image on the web page that I've called up. Can we get that? And here you can see exactly the same sorts of features. Craters covering each other up and burying each other's rays in blankets of new ejecta. These are really neat, Glenn, don't you think? Are you there in the hall for us to react to this and take us to the next step?
I'm right here, Serena.
Oh, great,
Those are
Glenn.
some pretty spectacular images. And speaking of other planets, we've got here probably the most famous meteorite in our collection, which we think is a piece of the planet that has most interest to humans, namely Mars, in terms of possibly finding life on other worlds. And this is the meteorite that a year and a half ago, scientists from NASA think they found evidence for ancient life on Mars. And so this is one of the most interesting meteorites that we have, and it has stimulated a phenomenal scientific debate. Tim, you want to tell us a little bit more about this meteorite?
Yeah, let's take an email question before we tell you the real story behind this rock.
Okay, we have a question here from email. Sit down, TC, or we can't see. Okay, thanks a lot, guys. How can you tell that the Mars meteorite is from Mars? Excellent question. The answer is that Mars meteorites, when they're ejected from the planet, are done so by events that cause partial melting and trap atmospheric gases from Mars. And you can tell that the atmosphere of Mars is very different from that of Earth, and we know what the gases are because they were measured by the Viking program in the 70s. Also, Mars is the only other planet with really young volcanism, and some of the ages of the meteorites from Mars are extremely young. And now, why are people now saying that it probably does not contain evidence of microscopic Martian life? Well, that's just science, folks. Sometimes we make initial discoveries that are very exciting, and then members of the community go in and restudy and think that perhaps the evidence is not as compelling as was first put forward. But in all fairness, the original article did not claim evidence for Martian life. That was what the press said in the result reacting to the publication of the paper. We got another email, which is coming up to the front. Okay. Stark County, do you have any questions while we're getting this email? Nope. Yes? Okay.
Yeah. Have as many meteorites hit the Earth as have hit the Moon?
Well, a lot of meteorites have hit the Earth, but the Earth has something that the Moon does not, plate tectonics. And so, except for the most ancient terrains, oh, and the other thing that the Earth has that the Moon doesn't is an atmosphere, which erodes and changes the surface of the Earth. So, in most continental terrains, over time, meteor craters are erased by erosion, and if they fall in the ocean basins, eventually those craters are subducted and carried down, and we don't see them anymore. In fact, the oldest ocean is only 200 million years old. So there's a preservation problem here on our planet. What is the blue powder? The two emailers want to know what the blue powder is. That is tempera paint mix, just sprinkled on with a sifter on top of white flour. Great experiment, huh? Okay, Okay, we're going to go to Tim and Glenn now, and we're going to hear a little bit more about Mars, I think, in armchair astronomy.
So, Tim, what else is so special about this rock?
Well, if you come to the National Museum of Natural History, you can see 6 of the 12 Martian meteorites that are known from the world's collections. You can do something really extraordinary. You notice I've taken the glove off, and you can actually reach in here and touch a piece of Nakhla, one of the Martian meteorites. But the one that even we don't touch, we don't even take it out of this little container it's in, is Allen Hills 8401. And it is really special. It's special because it's 4.5 billion years old. It formed shortly after Mars and is by far the oldest Martian meteorite we have. But it's also really special because if you look deep in the interior of this rock, and if I could have the first image, you see these little orange things. These are about 0.5 millimeter across, and these are carbonates. And these carbonates probably formed much later than 4.5 billion years, when Mars was warm and wet. And if you have warm and wet, what you might look for is life. And if we could have the next image. In 1996, a group of scientists at Johnson Space Center, people I actually worked with when I worked there, discovered these little things. These are tiny little objects that look like fossilized nanobacteria. To give you an idea of how small these are, one of them is about 1/millionth the diameter of a human hair, and so extremely small objects. And they argue that these might be possible indicators of ancient bacterial life. Well, if we come back to the rock, there's been a lot of debate about this, as Serena said from the email, and it isn't established yet whether that is or isn't ancient Martian life. but it's driving a lot of our desire to go back to Mars. Remember, we went there in 1976 and we got images like this from the Viking lander, and now we want to go back. And there are a lot of other places we want to go, and after we take some questions with Serena, we'll come back and tell you a little bit more about solar system exploration and meteorites' role in that.
We have an email question here. When did scientists first begin studying meteorites? I think that's a good question for Glenn. Glenn, when did scientists first begin studying meteorites?
Well, people began studying meteorites hundreds of years ago before they realized what they were. As recently as 200 years ago, people didn't believe that rocks fell from the sky. In fact, it's attributed to one of our earliest presidents, Jefferson, that he didn't believe that meteorites fell from the sky. And when a meteorite fell in Connecticut in 1803, he attributed that to the dishonesty of Yankee professors rather than rocks falling from the sky. But toward the later part of the 19th century, people began to realize that these really are things coming from the sky. But it wasn't until the 20th century when we really began to realize that these things are pieces of other worlds. And that when we study these rocks, we are actually studying those other worlds. And as we're going to talk about shortly, studying these actually poses questions that help drive the missions that NASA is sending up to visit the asteroids, comets, and other worlds. Back to you, Serena.
Okay, we have some questions here from the T.C. Williams bunch. Go ahead.
How does the atmosphere affect a meteor?
How does the atmosphere affect a meteor? Well, it slows it down. And that's probably the most important break on what makes a meteorite make a big divot out of Earth versus just a little burial. Annika from Indiana, just a sec. Annika from Indiana?
Okay, how can you tell if a meteorite is made in an asteroid or in a planet?
How can you tell if a meteorite is made on an asteroid or on a planet? Well, if a meteorite is made of the undifferentiated stuff, sort of these cosmic dust bunny or materials like the meteorite Allende that Glenn talked about, those are things that haven't formed planets. If a meteorite is an iron meteorite or is a silicate meteorite that shows evidence for melting, that means that a planet-like process affected it. But whether it was an actual planet-sized planet or just a little asteroid is very difficult to tell, and that's a big area of meteorite research. All right, I know we have a question here.
How many meteorites actually get through the atmosphere and actually hit the Earth's surface?
In what time period?
In like a year, maybe.
How many meteorites hit the Earth's surface in a year? I think that's a good question for Glenn. Glenn, how many meteorites hit the Earth's surface in a year?
Well, the number that actually make it to the Earth's surface is very small, a few tens, maybe a few hundreds. But the Earth daily is bombarded by thousands or millions of meteorites, but most of them are in the form of tiny dust particles so small that they hit the atmosphere and burn up almost immediately. So the vast majority of things that actually hit Earth never makes it all the way down to the Earth's surface. The intense friction from when they hit the atmosphere at high speed causes them to burn up almost immediately. So the number that actually reach the ground is very small every year, and the number that we actually find is even smaller than that. Back to you, Serena.
Okay, TC, do you have another question?
Yeah, I was just going to ask if size or the atmosphere makes a bigger difference for a meteor reaching the Earth.
Yes, size does have an effect. Below about the size of a bus or something like that, a meteorite doesn't make a very big divot. It's only when you start getting meteorites the size of this building or of Washington, D.C., that a meteorite really makes an impact, as we say. Ashley from Indiana, I hear you have a question.
Yes.
Turn your TV down.
That the meteorites came from the asteroid belt.
How do you know a meteorite forms in the asteroid belt? Well, some meteorites have been tracked back to the asteroid belt from their entrance trajectory. Others seem to match in their chemical composition the composition that's calculated for certain asteroids based on their physical characteristics observed by astronomy. But I'll turn this over to Tim for a little more explanation. Tim, how do we know that meteorites come from the asteroid belt, other than the two things I've mentioned?
Well, it's kind of a complicated thing. One of the things, as we showed you before, sometimes we have to go to very sophisticated analytical techniques. And one of these is called isotopes. Now, isotopes is sort of a dirty word among a lot of people, but it's a way of studying different kinds of the same material. For example, oxygen has 3 isotopes, and if you ratio them relative to one another, they basically become a fingerprint for where the object is from. Now, the reason we do this is because, of course, we haven't been to a lot of these places. We haven't picked up rocks from there. So we have to come up with sort of creative new ways to figure out where objects are from. But we're going to come back in just a little bit and tell you something about how we are going to figure out where rocks come from by actually going and getting them. So back to you, Serena.
That's right, Tim. We've had a lot of good questions here that tell us what we do know about meteorites in the solar system, but there's a lot more that we don't know than we do know. And not only do we need to study meteorites, those handy messengers from outer space that come to our own doorstep, but we ourselves need to go out and have more of a view of our solar system. And I think Tim and Glenn are going to tell us about new plans for exploration.
Thanks, Serena. Well, by studying meteorites, we've learned lots of things about our solar system, but as we said earlier, in some ways it's raised more questions than it's answered. But we're about to come up on some of the most exciting time in the history of planetary science, because NASA is getting ready to send some missions out to a variety of places in the solar system, in some cases to actually bring back pieces of those other worlds. Okay. And what we're finding...
We've got one more question that's coming in before we go on with this. So let's have the question. Lacey from Indiana.
Is there any recorded deaths caused by meteorites?
I'm sorry, I didn't understand the question. Did you get that, Serena?
So you need to turn
are there any recorded deaths from meteorites? No. I mean, you should be much more worried about walking to school and crossing the street. I know I'm much more worried about crossing Pennsylvania Avenue than I am about being struck by a meteorite. There are no recorded deaths from meteorites. So let's go back to Glenn.
So what we're coming up in the next 20 years, NASA is going to send some missions out to other worlds to bring back, in some cases, pieces of those other worlds. And studies of meteorites are actually driving where those missions are going to go. And this is going to be incredibly exciting. You want to tell them a little bit more about it, Tim?
Yeah. 2 of the ones that I'm really interested in, we're standing here for a reason, because this is the Apollo to the Moon case. And from 1969 to 1972, 12 U.S. astronauts actually set foot on the moon, and 3 Russian unmanned missions. And they brought back samples. And we're actually going to go get samples. The 2 I'm really interested in are the Mars missions. Probably in 2005, we're going to launch a mission to Mars that will bring rocks back in 2008. And for the first time, we'll actually have pieces of those samples in our laboratories. And in a few years, a joint Japanese-U.S. mission called MUSIS-C is going to go to an asteroid and bring samples back. And this is so exciting because, we can do a lot with meteorites, but until we actually have a piece of a rock and we know exactly where it's from, we really can't put those 2 together. And there are a couple of missions you're really interested in, Glenn, so why don't you tell us about those?
Well, the one I'm really excited about launches in about a year and a half, and it's called Stardust. And this is going to launch a spacecraft that's actually going to rendezvous with a comet, and it's going to collect dust from the coma that surrounds the comet. It's going to fly through the comet's coma, collect dust, and it's going to bring it back to Earth, and when it arrives in Earth's orbit, it's going to inject a small little capsule into the Earth's atmosphere, and it's going to fall to Earth in a parachute, so that we're actually going to be able to recover it and in our laboratory study actual dust from a comet. And this is about the oldest and most primitive material we think exists in the solar system and can tell us a great deal about the solar system's beginnings. That's going to be fascinating.
Well, what we have for you now is a montage of exploration images going from the past into the future, including rovers and landers and eventually human exploration. So we want to show you these. These are photos and artist concepts of where we're going in our solar system.
Well, that brings us to the close of our electronic classroom. And before I throw it back to Serena, I want to thank Serena and my colleague Tim here. We hope that you've learned today a little bit about how we can study our solar system and some of the science that goes on behind it. And I hope that you've also picked up on the fact that we really love what we do. This is actually very fascinating. And we do this science because it just gets us tremendously excited. And I hope that you have picked up on that and that it gets you interested in science as well. So now we're going to go back to Serena for some more question and answers. Serena?
Hi. Stark County, we're hoping that you have some questions. Are you there? Yeah.
How often do large meteorites hit the Earth?
How often do large meteorites hit the Earth? What do you mean by large?
The ones that cause the big craters,
like meteor crater? Or are you talking about meteor crater, or are you talking about the KT boundary? I mean, that's the KT boundary? Okay, well, we haven't had one for 65 million years. That's good. On average, though, in the geological record, big events that are between meteor crater and the KT boundary, are in about the 20 million year range. So they're not frequent, but when they happen, they really take a big divot, and that's, of course, a concern that is very important to biologists, because biologists are now working on ideas that might connect meteorite impacts with extinction events where a lot of biological organisms simply cease to exist. We now think the evidence is excellent for the Cretaceous-Tertiary boundary, but there are many more major extinctions that need to be explored in the light of the meteorite hypothesis. Stark County, do you have another question?
Yeah, I do.
Okay. What is your question?
Okay, you talked earlier about the impact that formed the moon. What evidence on the Earth do you have to support that?
What evidence on the Earth is there to support the formation of the moon? That's a pretty difficult question. I think that's a good question for Glenn. Glenn, what evidence is there on the Earth that supports this formation of the moon hypothesis? Not on the moon, but on the Earth.
But I'm afraid the reason we know the story does come from the moon. It comes from the rocks that the Apollo astronauts brought back. But it also has to do with the differences between the Earth and the moon. The Earth and the moon obviously are associated together in space, and they have interesting similarities that suggest that they have formed in a common process. And yet there's one very big difference between the Earth and the moon that's obvious just from looking at pictures of the two, which is that Earth is covered with water and with an atmosphere, and the moon is completely lacking in water and completely lacking in atmosphere. In fact, if you look at the minerals on the moon, even the minerals don't contain any water. The moon is just absolutely dry. And that suggests that the moon formed by a process that involved very, very high temperatures. And yet it must have formed by some process that involved the Earth. So that's why we think that this process, this collision between these two bodies that formed the moon, the material that was thrown off into orbit around the Earth that eventually became the moon, was a vapor. It was very, very hot, and it eventually condensed to form rocks. But the less condensable compounds like water and gases and even some elements like sodium, which boil at fairly low temperatures, those elements were lost to space, so that when the moon finally condensed, what was left in orbit around the Earth was a bone-dry, rocky world with no atmosphere and no water. So it's in the differences that we see between Earth and moon that give us a lot of the information and what we know about the Apollo moon rocks themselves. Come in, Aaron. We have a question.
How long did it take for asteroids to form from little particles of dust?
That's actually a very good question. And we're not entirely certain of the answer, but we believe from studying chondritic meteorites, like the Ienda meteorite that I showed you earlier, that probably the planets had achieved most of their present size within the first 50 million years after the solar system first started forming. So somewhere in that 50 million years, we went from dust grains to planets, which, if you consider that the solar system is 4.5 billion years old, that's a very, very short time to go through that process from grains to planets. Beth, come in. You have a question?
Yes. How many of
observatories are used to track Earth-crossing asteroids?
I didn't hear the question. I didn't understand the question.
How many observatories are used to track Earth-crossing asteroids?
Not very many. I don't know the exact number, but it's on the order of probably a dozen or less around the world using to track Earth-crossing asteroids.
And there are no dedicated observatories to tracking Earth-crossing asteroids. Just like any other field of astronomy, those people have to apply for telescope time and try to get it. And sometimes it's very difficult for these projects because it's basically what we call a fishing expedition. You're not sure what you're looking for. So we really don't have as many, and many of the people who think that we should track these as a threat to Earth, what they're really saying in some ways is that what we need to do is learn more about these objects, and we can only do that if we know where they are.
Serena, back to you.
I understand we have another question. Go ahead. Who do we have?
Brian from Massachusetts.
Brian from Massachusetts. Are you there?
Hello.
Hi, Brian.
Hi.
What's your question?
I have a question. It's not about a meteorite or anything, but it's about an atom.
It's not about a meteorite?
Well, I have a question about an atom.
A question about what?
An atom.
An atom. An atom.
I've always been curious what
Yes?
an electron is actually made out of.
What is an electron made out of?
Negatively charged
This is
particles.
definitely a Serena question.
Okay. Your question is,
electron made out of?
your question is, what is an electron made out of? Golly, I wish I'd studied my physics a little better now. I used to know this one. Maybe Glenn remembers from his physics class. Glenn, what is an electron made out of? It doesn't have any mass, but it has charge. Has anybody done any work on that recently here?
Well, we don't work on atomic physics here at the museum, Serena. That's of course for laboratories like Stanford Linear Accelerator and Brookhaven and Argonne. And I really want to thank you for this question, Serena. I was looking forward to answering this one.
We just use them. We don't know what they're made of. So.
But we do know that an electron shares many properties in common with light. It behaves in part like a particle, and it behaves in part like light. And its properties, its movement and its properties can actually be described in part by the same physics that we use to describe light waves. That doesn't completely answer your question, I know. But it's also true that I don't think we really know in detail what an electron is made of.
Okay, Ashley? We have a question from Ashley, is that correct? Ashley, are you there?
Yeah.
What is your question?
How long does it usually take before a meteorite hits Earth?
How long does it usually take before a meteorite hits Earth? From when it leaves the asteroid belt or from when it enters the atmosphere?
When it leaves.
When it leaves? Well, it can take a very long time depending upon how it was knocked out of the asteroid belt, because a lot of meteorites are in Earth-crossing orbital patterns. You see them during the summer. There are families of meteorites that come out in August, and you see them in the middle of August, for example. There are swarms of meteorites that come in Earth-crossing orbits, but they come every year, and that means that they themselves are orbiting around. So you can't really predict when any given meteorite will actually hit the Earth from when it was knocked out of the asteroid belt. But once it enters the atmosphere, it's not very much time. Okay, Sabrina? Do we have a question from Sabrina?
Yes. What was the largest meteor ever found, and where was it found?
What was the largest meteorite ever found? Ever recovered? The largest meteorite ever recovered? Okay, I believe that Tim is our large meteorite expert. Tim, what is the largest meteorite ever recovered? I bet it was Gibeon, isn't it?
It wasn't Gibeon, in fact. It depends on how you look at the world. If you're talking about one single mass, the largest meteorite ever, and I'll use the word recovered because we don't have this one in captivity, is called Hoba. It weighs probably more than 60 tons. There are old pictures of 5 grown men standing on top of this thing, and it's still in the same place it was found in southern Africa. And, you know, we have a lot of smaller ones, but we've never managed to capture that one. So that about ends our field trip. We appreciate all the calls. They were really great questions. So let's go back to Serena.
Yes, and I want to add that we all want to thank the students of T.C. Williams High School, the world's best golf ball droppers, and the students in Stark County, Ohio. Guys, are you there? Saying goodbye? Thank you all very, very much. Yes, goodbye. Goodbye. And now I want to come down to earth. The last part of the field trip is telling you about the next one. And I think my colleagues Jim Blur and Dick Fisk are two very earthy types who can tell you something important.
Well, we've been on 2 field trips thus far. The first to gems and minerals, the second to meteorites and outer space.
You know, every time I see our gem and mineral collection, I'm just amazed at how perfect and beautiful and dazzling all those specimens are. But there's something kind of unsettling about it. I mean, what are the chances of a normal person ever finding a mineral or a gem like that, ever finding a ruby or a diamond?
Well, you know the answer. It's just about 0. But the same holds for meteorites. These are glorious objects, but do you think you'll ever find one in the city park or out in the field in the countryside? I don't think so.
And that's the real beauty of this third field trip, Stories in Stones, because here we literally get right down to earth. We talk about the normal rocks that make up the surface of our planet, the kinds of rocks that you can find right in your own neighborhood.
And you may be surprised to learn that each and every one of these rocks tells a story about the history of the Earth and the processes that operate on the surface of this planet.
So we invite you to join us on the third field trip, where we learn about volcanoes and earthquakes, and how large continental collisions have formed our planet's mighty mountain ranges. And we'll also help you learn how to read the stories in stones, the same way geologists do.
So come along for this fantastic story of active Earth.